Hey folks, I wanted to leave you with an explanation of question number 7 on the conservation of energy problem set. This is the graph. This is a graph that I had you do based on this problem about the cart getting plungered up the ramp. And I go over this one specifically because it's very hard to get every aspect of this graph correct. And so I just wanted to talk about it. And you can always send me questions. So the first thing to talk about, even before we do anything, is to say that the point of this worksheet was conservation of energy. And so that means that the mechanical energy is constant. So I drew mine in pencil. And so the mechanical energy is going to be the same value for the entire event. So it's a flat line no matter what. One thing that a lot of people don't understand is that you need to use the entire graph for your lines, because this negative 3.5 up here in the previous question, it says that the plunger extends 3.5 centimeters. So if you kind of like imagine what's going to happen, this is with the plunger extended. If I like compressed the plunger into the cart would go down to the brick. In other words, the cart would actually be at a position of negative 3.5 centimeters. And then when the plunger extended at its most extended, the cart would be 3.5 centimeters away from the brick, and that's where we set the 0. And then when it goes up the ramp, it ends at a position 75 centimeters away from this point. So really it travels like 78.5 centimeters. We kind of fudged a little bit, honestly. But I will tell you that extra 3.5 centimeters doesn't mean a whole heck of a lot. If I do this honestly, this should be negative 3.5, and this should be 71.5 centimeters. Whoops. But back to my point. If I compress this plunger, the cart would go back down to the bottom, and it would essentially be at a position of negative 3.5 centimeters. So this graph needs to go from negative 3.5 centimeters to 75, because there's energy stored at this location and again at this location. So the first line that I want to tackle is the elastic potential energy. So I drew that one in green, and of all of them, that's probably like the easiest one to describe what's happening. The beginning of this problem is when the cart has the plunger compressed, and so that means that the maximum amount of elastic potential energy is stored in the spring. At the same time, when the cart is all the way down at the bottom, it is not moving, which means it has no kinetic energy, and it's at the lowest part possible on the track, which means that there's no gravitational energy, potential energy being stored. So we start at a moment when the elastic potential energy represents the entire mechanical energy stored in the system. So that's why it starts up there. And then from a position of negative 3.5 to 0, that is the distance over which the plunger extends. Once the cart gets to a distance of 0 or a position of 0, the plunger loses contact with the brick. So the cart pushes away, and then once it gets far enough away, the whole system starts to move. This line should then go from the maximum to 0, because once the plunger is extended, it has released all of that elastic potential energy because that spring has uncompressed. So it goes from its maximum to 0. This line has to be curved because of the equation for elastic potential energy. It's 1/2 kx squared. And since the x-axis is position, it's basically saying that there's a second power, what am I trying to say? That the energy stored in the elastic potential energy is proportional to x squared. And so this has to have a quadratic shape to it, or a parabolic shape to it, as the energy goes down to 0. Because the spring is at its maximum compression, that's kind of like out to the side of a parabola, and so you get this drastic increase or decrease first, and the decrease slows to 0. kind of making it a smooth transition, and then the elastic potential energy remains zero for the rest of the problem because that spring is all uncompressed. The next one that's kind of easy to explain is the gravitational potential energy. For that one, again, the cart is at the base of the ramp, and then as that plunger compresses, for the entire remainder of the problem, the cart is moving up the ramp. So this one has kind of a funny shape. It has this like small increase at the beginning, and then it has a more regular large increase. I would probably say that this segment of this graph is the one I am least confident on, but I think I did it right. That there's a curve to it because there's again a parabolic decrease in elastic potential energy. There should be a similarly parabolic increase in gravitational potential energy. On the other hand, when this is happening, it's increasing at a rate that's proportional. The gravitational potential energy is kind of driving this part of the problem, and so that energy is proportional to height, and so the height is increasing at a regular rate there. It ends at the maximum, so it's ending when it's equal to the mechanical energy, because at the end of this problem, the only energy left is gravitational potential energy. It's not moving, and the spring is released, so there's no more other types of energy. The only thing that's left is kinetic energy, and so kind of because the elastic potential energy has a parabolic shape to it, the kinetic energy will also have a parabolic shape to it. The thing that I would say, like, someone who's going to get this mostly right might miss this one, that the kinetic energy can't go all the way up to the maximum, because when the plunger is fully extended, technically speaking, the cart has moved up the ramp already. And that means it has stored a little bit of gravitational potential energy. And so it's only the difference between the mechanical and the gravitational that the kinetic can get to. So it goes up with that quadratic shape to it. And then because after that, the gravitational potential energy is gained steadily, the kinetic energy is lost steadily. So even though it's 1/2 mv squared, the kinetic energy is proportional to the distance traveled up there. And so that's this graph of the 3 types of energy and the overall mechanical energy. Please send me questions as you have them, and you can always ask about it again when I see you next. Thanks.